there is a number that describes exactly how advanced a civilization is. It has nothing to do with intelligence. It measures only one thing: how much energy a civilization controls, how much of its world's available power it has learned to gather, store, and use. By that number, Earth has not yet finished its first stage of development. We sit, at this moment, at roughly 0.73, closer than it sounds, farther than it feels. The number was calculated only recently, using advanced machine learning models trained on the most current global energy data available. The exact decimal varies depending on which year's measurements are used and which formulas are applied. Some calculations place it slightly higher, some slightly lower, but the broad reading is the same. We are roughly 3/4 of the way to the first major checkpoint on a scale that runs much further than the first. The scale itself is older than the calculation. It was proposed in 1964 by a Russian astrophysicist named Nikolai Kardashev in a short paper with a long title. He was searching at the time for signals from other civilizations elsewhere in the galaxy, and he needed a practical way to think about what kind of civilization might be powerful enough to produce signals strong enough to find. His answer was a simple framework: 3 categories. A civilization that has mastered the energy resources of its home planet. A civilization that has mastered the energy resources of its home star. A civilization that has mastered the energy resources of its entire home galaxy. 3 thresholds. 3 jumps in scale, each one so large that the next made the previous look almost ordinary by comparison. Earth, by every reasonable measurement, has not yet reached even the first of those thresholds. The current trajectory suggests we may cross 3/4 of the way there by the year 2060. It could take another 300 years after that, or more, to actually complete the climb to a true Type 1 civilization, possibly faster, if artificial intelligence continues to accelerate research the way it has begun to over the past few years, possibly slower, if any of the risks accumulating in parallel produce a serious disruption. The exact timeline cannot be predicted. The general direction can. What we are going to do, across the hours that follow, is walk that scale from beginning to end. We begin where Earth actually stands, not where the imagination wants to put it. From there, we look carefully at what completing the first threshold would require. Which technologies, which engineering problems, which timescales? That question opens immediately onto a second one, asked first by a physicist named Enrico Fermi at a research lab in 1950, and never fully answered since. If civilizations like ours are possible, and the universe has had billions of years to produce them, where is everybody? Why does the night sky show only natural light, never artificial? That question, in turn, leads to a framework for thinking about what might be filtering civilizations out before they become visible at all. A framework that asks us to consider, soberly, whether the danger sits behind humanity or ahead of it. Only then, with that caution properly in place, do we allow ourselves to imagine what lies beyond the first threshold. A civilization that has learned to harness not a planet, but a star. And beyond that, the final, almost unspeakable scale, in which a civilization commands the resources of an entire galaxy. This is a story of patience, as much as it is a story of energy. The climb described across these chapters is not the kind of thing that completes within a single human lifetime, or within the recorded span of a single civilization, or within any time scale that allows for impatience. The smallest jumps on the scale require centuries. The largest may require millions of years. The version of Earth that exists when Type 1 is finally completed, if it ever is, will not remember most of the people listening to this tonight. The version that begins Type 2 will not remember any of them. And the version that approaches Type 3 will be related to the people now alive. This does not make the climb meaningless. It makes it long. There is a difference. And it is the difference we will try to hold on to throughout. We begin where the climb itself actually begins, not with stars, not yet with galaxies, with a single number that describes a single planet at a single moment in its very long history, 0.73. The current position of an entire civilization on a scale that almost no one alive today thinks about on most ordinary days, but that quietly measures everything humanity has built across the past 2 million years and everything it might still build across whatever time remains ahead. The climb has been going on for longer than any of us have been alive to see. It is not finished. It is, in many ways, only beginning. And the part still ahead is, by every measure available, the more interesting part of the entire story. Before we look at what Earth could become, we should look at what Earth currently is. Not in the way a history book describes a civilization, by counting its empires, its inventions, or its names. There is a different way of measuring a civilization, a quieter one, a more mathematical one, and by that measurement, Earth has a number. The number is 0.73. That is where Earth sits, tonight, on a scale that was built specifically to measure how advanced a civilization is. Not how clever, not how wise, not how kind. The scale measures one thing, and one thing only. It measures how much energy a civilization controls, how much of its world's available power it has learned to gather, store, and use. And by that measurement, Earth has not yet finished even the first of 3 stages. The number itself comes from a fairly recent calculation. Within the past few years, scientists used advanced machine learning models to estimate where humanity actually falls on the scale, given its current global energy use. The math returned an answer: 0.73. Some calculations place the figure slightly higher, some place it slightly lower. The exact decimal varies depending on which year's energy data is used and which formulas are applied. But the broad picture is the same. We are roughly 3/4 of the way to the first major threshold. We are not at the first major threshold, and the distance still remaining, although smaller than the distance already crossed, is in some ways the most difficult portion of the climb. To understand what that number means, we have to look at where it comes from. The scale itself has a name. It is called the Kardashev scale. It was proposed in 1964 by a Russian astrophysicist named Nikolai Kardashev in a short paper published under a long title: Transmission of Information by Extraterrestrial Civilizations. The paper was not written as a roadmap for humanity's future. It was written for a different purpose entirely. Kardashev was part of a team of scientists looking, during the early 1960s, for radio signals from other civilizations. The search was new at the time. Radio astronomy had developed enough that, in principle, it should be possible to listen for artificial transmissions coming from elsewhere in the galaxy. The question Kardashev was trying to answer was a practical one. If another civilization were out there, transmitting signals strong enough to cut through the natural noise of the universe, how powerful would those signals have to be, and what kind of civilization would be capable of producing them? His answer was a simple one. To produce signals that strong, a civilization would need to control extraordinary amounts of energy. Not the kind of energy used to run a city or even a continent. The kind used to run a planet or a star or eventually an entire galaxy. Kardashev proposed 3 categories in order of increasing scale. A Type 1 civilization was one that controlled and used all the energy resources of its home planet. A Type 2 civilization controlled and used all the energy resources of its home star. A Type 3 civilization controlled and used all the energy resources of its entire home galaxy. 3 rungs, 3 categories, 3 jumps in scale, each one so large that the next made the previous look almost ordinary by comparison. Kardashev did not propose these categories as predictions. He did not say humanity would ever reach them. He proposed them as a framework, a way of describing what an advanced civilization might look like from a great distance, in terms that did not depend on language, biology, or any other detail that might vary from one species to the next. Energy is universal. The amount used can be measured, and anything that can be measured can, in principle, be compared. Now, in the years since that paper was published, several other researchers have refined the original scale. Carl Sagan, in particular, suggested that a strict three-step system was too coarse, since civilizations do not jump from one stage to another. They climb slowly, fractionally, in small increments. Sagan proposed extending the scale into decimals, so that a civilization in the middle of a transition could still be located somewhere on it. This is how Earth ended up with a number like 0.73. Not because we are nearly type 1, we are not, but because we have crossed enough of the distance, in fractional terms, to be measurable. The scale is logarithmic, which means each whole number represents roughly 100,000 times more energy use than the one before it. Even a small decimal shift on this scale represents a large amount of additional energy in absolute terms. To put that in concrete numbers, a true Type 1 civilization would need to control somewhere in the range of 10 to the 16th power watts of energy. Humanity, at present, uses something closer to 10 to the 13th power watts. The gap, in raw terms, is roughly 200,000 times. That sounds enormous. And in absolute terms, it is. But on the Kardashev scale, which compresses these enormous numbers into a logarithmic measurement, we have already covered most of the visible distance. The remaining quarter is the harder part. It nearly always is. There is a quieter point worth noting here before we move on. The number 0.73 did not arrive overnight. It is the result of a very long climb. The first hominid who learned to control fire, somewhere around 2 million years ago, took the first measurable step on this scale, even though no one at the time understood what they were doing or where it would lead. Every transition since, from agriculture to the steam engine to electricity to nuclear power, has been another small fractional increment. The climb has not been steady. It has accelerated sharply in the past 2 centuries, especially since the beginning of the industrial era. But the broad direction has been the same for as long as humans have been measuring energy at all. It is worth lingering on that 2 million year span for a moment, because it is easy to read past it without feeling its actual weight. 2 million years is longer than the existence of every named civilization in human history, combined by an enormous margin. It is longer than the time that has passed since modern humans first emerged as a recognizable species. It is longer than the time since most of the world's deserts were last green. The control of fire belongs to a different species than ourselves. Homo erectus, in the most commonly accepted reading of the evidence, a hominid whose brain was smaller than ours, whose body was differently proportioned, whose face would not be entirely familiar in a crowd. And yet, that hominid is the one who took the first step on the scale we are now using to measure ourselves. For most of the time since that first fire, the climb proceeded so slowly that it would not have been visible to anyone living through it. Generations passed. Communities formed and dispersed. The slow accumulation of knowledge about how to feed a fire, how to bank it overnight, how to carry an ember from one place to another, how to cook with it, how to harden tools in it, would have looked like ordinary daily practice to the people involved. None of them would have understood that they were participating in something measurable. None of them would have understood that the small skill being passed down from parent to child was, in its own way, the beginning of a line that would eventually reach the calculation of a logarithmic scale measuring energy consumption in watts. The line is real, even if no one walking it could see it. Agriculture, beginning roughly 12,000 years ago in several regions of the world independently, was the next major increment. Farms allowed populations to grow larger than the surrounding land could have supported under hunter-gatherer conditions. Larger populations allowed for specialized labor. Specialized labor allowed for more sophisticated tools, including better methods of harnessing animal muscle, water flow, and wind. Each of these was a small fractional shift on the scale. Each was nearly invisible at the time. The shift began to accelerate, in any historically obvious sense, only with the beginning of the industrial era. The development of efficient steam power in the 18th and 19th centuries allowed humans for the first time to convert stored chemical energy in coal into useful work at scales no earlier civilization could have approached. The development of oil-based fuels added another large increase in the early 20th century. The development of nuclear power, which began as a weapons program and only later expanded into civilian energy production, added another sharp jump in the middle of the 20th century. And the development of large-scale renewable systems, primarily solar and wind, has begun adding further increments across the past several decades, though the pace and unevenness of that development is still being negotiated, region by region, year by year. All of that together, 2 million years of climb, with most of the visible motion compressed into the past few centuries, produces a single number, 0.73. There is one more way to hear that number, and it is worth carrying forward into the chapters that follow. 0.73 is the distance covered, expressed as a fraction, but it is also, in a different reading, the distance still remaining. From this position on the scale, there is no shortcut to the top of the first threshold. The remaining quarter of the climb has to be traveled, the same way the first 3 quarters were traveled, one increment at a time. The technologies that will close the gap, fusion, large-scale renewable systems, efficient storage, the deeper kinds of grid integration that make energy abundant rather than only available, are already partly built. None of them are finished. None of them have reached the scale required. The remaining work is real work, and it will be done, if it is done at all, slowly, the way every part of the climb has been done so far. The honest position, then, is this. We are closer than we have ever been to crossing the first major threshold on a scale that runs much further than the first. We are not at the threshold. The climb is not finished. And the questions that lie beyond the first threshold, the questions of what happens next, are the questions I am going to spend the rest of ours carefully walking you through. For now, that is enough. We hold a number, 0.73. We hold a name, the Kardashev scale. We hold the broad sense that humanity is on a long, slow climb that began 2 million years ago and has not yet crossed its first major checkpoint. The rest of the climb begins to make sense only when we look more carefully at what completing the first stage would actually involve. That is the work of the next chapter, and we turn to it now. What the number tells us, in the most honest reading, is that humanity is closer to its first major threshold than it has ever been, and still some distance from actually reaching it. Most recent studies suggest that humanity will reach about 3/4 of the way to Type 1 status by the year 2060, and that the full completion of Type 1 could take another 300 years after that. Possibly more, possibly less. The estimate depends on assumptions about energy adoption, technological progress, and a large number of variables that no one can predict with full confidence. There is no ceremony for crossing the threshold. There never has been for any earlier energy transition. The shift from wood to coal, the shift from coal to oil, the shift from oil toward renewable sources, none of these happened on a particular date that anyone living through them could circle on a calendar. They happened gradually, across generations, until at some point the world looked back and realized the transition had already taken place. The climb toward Type 1 will almost certainly follow the same pattern. There will be no headline, no formal announcement, only a slow, distributed accumulation of capacity until one day a future generation looks back and finds that the threshold has quietly been crossed. This is what Earth currently is, in the language of the Kardashev scale. Not a civilization on the verge of something dramatic, not a civilization standing at the edge of a stage, a civilization slowly approaching the first of three thresholds, on a scale that extends much, much further than the first. What follows from here is the rest of that scale. Type 1, in its fully realized form, and what it would take for Earth to actually complete it. Then a question that arrives almost automatically once you start thinking at this scale. If civilizations like ours are possible, where is everyone else? From there, a careful look at the more uncomfortable answers to that question and the framework that has emerged to make sense of them. And finally, the two thresholds that lie beyond Type 1, each one larger and stranger than the last. For now, all we need to remember is the number, 0.73. The current position of an entire planetary civilization, on a scale that runs much further than most people ever consider it. The climb has been going on for 2 million years. It is not finished, and the part still ahead is, in many ways, the most interesting part of the entire story. A Type 1 civilization is the first true milestone on Kardashev's scale, and the only one of the three that does not require leaving the home planet. Everything required to achieve it exists, in principle, on Earth itself. The sunlight that strikes the surface every day, the wind across the oceans, the heat rising from beneath the crust, the pull of the moon on the tides, the energy stored in nuclear fuel, the energy still locked, for now, in fossil reserves accumulated over hundreds of millions of years. All of it, in some combination, captured, stored, and put to use, with very little waste. That is the full definition. A civilization that uses all the energy available to it from its own planet, and uses it well. It is worth pausing on what that actually involves, in concrete terms. The sun, on its own, delivers to Earth's surface roughly 170,000 terawatts of solar energy at any given moment. The total amount of energy currently used by all of human civilization, at full operation, is closer to 18 terawatts. The sunlight reaching the planet in a single day carries more usable energy than humanity has consumed across its entire industrial history. The constraint, in other words, has never been the supply. The supply has been there all along. The constraint has been the difficulty of catching it, holding on to it, and moving it to where it is needed. A Type 1 civilization closes that gap. Not perfectly. Some energy will always be lost. Some heat will always radiate away, regardless of how carefully the systems are built. But close enough that the question changes. Energy stops being the limiting factor on what a civilization can do, and something else takes its place. Materials, perhaps, or time, or the much harder question of how to use abundance well, once it finally exists. Several pathways have been proposed for how Earth could actually arrive at Type 1 status. None of them are simple. None of them rely on a single breakthrough. The honest picture is one of slow, layered combination. Solar capture remains the most discussed component, covering meaningful fractions of the world's deserts, where sunlight is most abundant and land is least contested, with collection arrays large enough to gather a significant percentage of incoming solar radiation. The technology to do this exists. The challenge is one of scale and integration, manufacturing collectors at the rate required, transmitting the gathered energy from remote regions to where it is needed, and storing enough of it to cover the hours when the sun is set or the seasons when output drops. Storage is the quiet bottleneck of nearly every Type 1 proposal. A planet's energy needs do not pause at sunset. They do not slow during a still week with no wind. A civilization that wants to run on captured planetary energy needs a way to bank the surplus from abundant hours and draw on it during scarce ones, at a scale far beyond anything currently built. Battery technology has improved considerably across the past 2 decades. It is still not close to what would eventually be required at full planetary scale. There are several proposed approaches to the storage problem, each with its own strengths and limitations. Conventional batteries, the kind that power phones and electric vehicles, can be scaled up into grid-scale installations, and increasingly are. They are limited by the materials they require, and by the slow degradation that comes with repeated charging and discharging across years. Pumped hydroelectric storage, which uses surplus energy to pump water uphill into reservoirs, and then releases that water back through turbines when energy is needed, has been used at industrial scale for decades. It is reliable. It is also geographically limited, since not every region has the topography to support it. Newer approaches include compressed air storage in underground caverns, thermal storage in molten salt or in heated rock, and various forms of chemical storage, including the conversion of surplus electricity into hydrogen or other fuels that can be stored long-term and converted back into electricity when needed. None of these approaches, by itself, solves the planetary scale problem. Together, layered carefully, they begin to. The work of layering them is unglamorous engineering. It does not photograph well. It does not produce dramatic announcements. It accumulates year by year in installations that most people never notice unless they happen to drive past one. Geothermal energy contributes a different kind of promise. It does not depend on daylight, weather, or season. The heat rising from inside the earth flows continuously, day and night, in every climate. The challenge is reaching it efficiently in regions where the crust is thicker. Engineers have begun developing what is sometimes called enhanced geothermal, which uses deeper drilling to access heat in places where the surface does not obviously cooperate. The early projects exist. The full scale does not yet. Tidal energy, wind capture, and other smaller sources add their own contributions. None of them, individually, would carry a civilization to Type 1. Together, layered carefully across decades, they begin to resemble the kind of total system that a Type 1 civilization would require. There is also the matter of fusion. For most of the past century, the dream of practical nuclear fusion, the same process that powers the sun, has been just a few decades away. It has remained just a few decades away for so long that the phrase itself has become a quiet joke among physicists. But there are reasons to think the dream is closer now than it has ever been before. The reasons have less to do with raw physics, which has been largely understood for some time, and more to do with a particular tool that has recently entered the field: artificial intelligence. Scientists at the United Kingdom's Atomic Energy Authority have begun using AI supercomputers to help accelerate fusion research. The systems involved in fusion are extraordinarily complex. The plasma inside a fusion reactor behaves in ways that are difficult to model and even more difficult to control. Earlier generations of fusion researchers had to test their hypotheses slowly, one experiment at a time. Across years of careful work, the newer AI tools can model thousands of variations in the time it would have taken to test one of them physically. The pace of fusion research has shifted perceptibly in just the past few years. This is not the only example. A team at DeepMind, a research laboratory focused on artificial intelligence, recently announced that one of their systems had identified the structures of millions of new inorganic crystals. Many of these crystals could plausibly be used in new energy storage systems, new solar collectors, new conductors. Researchers estimated that the work the AI had completed was the equivalent of roughly 800 years of human research effort, compressed into a much shorter span of time. Some of those crystals will probably turn out to be impractical or unstable. Others may form the basis of technologies that change the climb toward Type 1 in ways that current estimates do not fully reflect. This raises a possibility worth sitting with carefully before moving forward. The earlier estimates for reaching Type 1 status, which suggested perhaps 3/4 of the way by 2060 and the full threshold another 300 years after that, were calculated under assumptions about the speed of scientific research that may already be outdated. If artificial intelligence continues to accelerate fusion research, materials science, grid optimization, and the dozens of other supporting fields required to complete the climb, the timeline could compress significantly. It could also extend, depending on how the same technology interacts with the various risks that will be discussed later video. There is a quiet asymmetry in this situation that is easy to overlook. Every century before this one moved on a relatively predictable trajectory. The pace of research was set by the number of researchers available, the tools they had to work with, and the time required to test their hypotheses one at a time. The pace was slow. It was readable. Forecasters could estimate, with reasonable confidence, where energy technology would be in 50 or 100 years by extrapolating the curves of the previous 50 or 100. That kind of forecasting becomes much harder when one of the underlying variables, the rate at which research itself can proceed, is being directly altered by a new kind of tool. Predictions made before the rise of capable AI systems may no longer apply in either direction. The arrival could be earlier than expected if the acceleration holds, or it could be later if the same technology produces complications that consume the time it would have saved. This uncertainty is, in some ways, the honest signature of every major transition in the history of energy technology. The arrival of the steam engine was not predicted accurately by anyone living through the early years of its development. Neither was the arrival of electricity or nuclear power. Each one was projected to grow more slowly than it actually did, and then projected to plateau earlier than it actually did. The pattern is consistent enough that it would be unusual for the current transition not to follow it. The climb toward Type 1 is likely to surprise people living through it in both directions. The exact shape of the surprise is, for now, hidden. For now, set those risks aside. Imagine, for a moment, that the climb proceeds cleanly. That fusion is solved within the next century. That storage technology scales up to the level required, that the political and economic coordination involved actually holds across the generations needed to complete the project. What would a fully realized Type 1 civilization actually look like from the inside? The most direct change would be the end of energy scarcity in any meaningful sense. Power in such a civilization would be effectively abundant. The vast majority of current human conflicts that center on energy access, oil, gas, electricity, would lose their original reason for being. This does not mean conflict would end. Civilizations find other things to argue about, but the particular pressure that drives so much of current geopolitics, the competition for fuel, would no longer apply. Climate, in a Type 1 civilization, would not be left entirely to chance. With enough energy available, large-scale interventions become possible. Carbon removal from the atmosphere at meaningful scale, active management of regional weather systems, restoration of ecosystems that have suffered through earlier, less efficient, industrial eras. None of these are guaranteed. A Type 1 civilization might still choose not to do them, but the energy required would no longer be the obstacle. Daily life in such a civilization would not necessarily look futuristic in the way science fiction has tended to imagine. The buildings might look similar, the streets might look similar. The fundamental shapes of human existence might not change as much as the underlying systems beneath them. What would change is what is possible. Universal access to clean water, achievable through energy-intensive desalination at any scale required. Universal access to food, achievable through controlled environment agriculture in regions that currently cannot support farming. Universal access to medical care, supported by energy budgets that no longer place artificial limits on how widely advanced treatments can be distributed. Deserts could be irrigated. Communities could exist comfortably in places that currently struggle. The pressure that scarcity places on every difficult human choice would loosen. There would also be, almost certainly, the beginning of a real human presence beyond Earth. Not large colonies, not entire populations transferred elsewhere, but outposts, research stations on the Moon, initial bases on Mars, industrial mining operations in the asteroid belt, None of these would necessarily make Earth a multi-planet civilization in any complete sense, but they would represent the first steps in a direction that becomes more important at the higher Kardashev levels. The political shape of a Type 1 civilization is harder to predict than the technological one, but a few patterns suggest themselves. Many of the current borders that organize human politics are organized around resource competition, oil reserves, water access, arable land, strategic geography. A civilization that has solved the underlying scarcity behind those competitions would not automatically become peaceful, but it would no longer be fighting over the same things. The shape of cooperation, if it exists at that scale, would likely look more like a network of coordinated regional governments than a single global authority. Earlier predictions of unified world government have generally underestimated how stubbornly local identities persist. Local identity does not require scarcity to survive. It survives on language, geography, history, and shared memory, none of which energy abundance directly affects. A Type 1 civilization, viewed from a great distance, would also begin to look different. Its radio signature, the total amount of artificial electromagnetic noise it produced, would be measurably larger than anything Earth currently broadcasts. Its infrared signature, the waste heat radiating from its energy infrastructure, would be detectable in ways that current Earth simply is not. If another civilization were watching, they would see a planet that had crossed a threshold. They would see what they themselves, perhaps, had crossed at some earlier point. There is a quiet thought that hangs over this entire chapter, and it is worth naming directly before moving forward. The path described here is not guaranteed. It assumes that humanity completes the climb to Type 1 cleanly, without major interruption. It assumes that the technologies required arrive in time, that the political coordination required holds together across centuries, that the various risks accumulating in parallel with the climb do not produce a catastrophic disruption along the way. Each of those assumptions could fail. The next chapter takes up exactly the question of whether such failures are likely, and if so, why we appear not to see any sign of other civilizations that succeeded where we might fail. This chapter has described what a successful completion of Type 1 would look like. The next chapter asks the harder question of whether successful completion is rare. This is the version of Earth that lies at the end of the first stage. Not utopia, not paradise, not a civilization without problems, just a civilization that has finished one particular climb and now stands at the edge of an entirely different question. Because if reaching Type 1 is possible, and humanity is genuinely capable of it within a few centuries, then a different question becomes pressing, a question that does not concern us alone. It concerns everyone, everywhere, who might ever have tried this before. And it is the question we turn to next. In the summer of 1950, at a research laboratory in Los Alamos, New Mexico, a small group of physicists sat down together for lunch. The conversation, by most surviving accounts, began lightly. It drifted through the usual subjects of physicists eating together. One of the topics that came up was a cartoon that had appeared in a recent magazine, joking about flying saucers. The conversation moved on. Other things were discussed. And then, somewhere in the middle of the meal, one of the men at the table, the Italian physicist Enrico Fermi, asked a question that the others did not at first know how to answer. The question, as it has been remembered, was a short one. Where is everybody? There are several versions of exactly how Fermi phrased it, and his colleagues recalling the moment decades later did not all agree on the precise wording. But the meaning was clear enough, and the implication carried weight even before anyone responded. Fermi was not asking about lunch companions. He was asking about the universe. If life is possible at all, and if it has arisen here on Earth, and if the universe is as old and as full of stars as astronomers have been describing it, then somewhere out there, on some other world, life should have arisen as well, possibly on many other worlds, possibly on most of them. Some of those civilizations, given enough time, should have advanced far enough to leave evidence, to build something, to send something, to make some kind of mark that we could see from here. And yet, looking around the universe with the best instruments available, we see nothing. This is the Fermi paradox. It is not a theory. It is not a prediction. It is a quiet, persistent contradiction between two things that both seem to be true. The universe is enormous and old, and apparently capable of producing life. And we have found, despite careful searching, no convincing evidence that any other civilization has ever existed anywhere at any point in cosmic history. To understand why this contradiction has stayed troubling for as long as it has, it helps to look at the numbers involved. Estimates of the total number of planets in the Milky Way galaxy alone range from 1 or 200 billion at the conservative end to 1 trillion or more at the upper end. Many of those planets sit in orbits that would allow liquid water to exist on their surfaces. Many of them are made of the same kinds of elements as Earth. None of this guarantees life, but none of it makes life impossible either. In the years following Fermi's lunchtime question, several attempts were made to put numbers to it. The most well-known came in 1961 from an astronomer named Frank Drake, who proposed a formula that has carried his name ever since. The Drake equation does not produce a single answer. It produces a framework. It takes the total number of stars in the galaxy and multiplies it by a series of fractions. The fraction of stars with planets, the fraction of those planets that are habitable, the fraction of habitable planets where life actually arises, the fraction of life-bearing planets where intelligence eventually develops, the fraction of intelligent civilizations that build communicating technology, and, finally, the average length of time such a civilization remains capable of being detected. The answer the equation produces depends entirely on what numbers you put into it. Optimistic estimates suggest there should be hundreds of detectable civilizations within our galaxy alone. Pessimistic estimates suggest there might only be one: ourselves. The equation does not solve Fermi's paradox. It simply puts shape to it and shows where the uncertainty lives. Most of the variables are not yet known with any precision. The search for evidence has continued in parallel with the math. Beginning in the early 1960s, around the same time Drake was first writing his equation, astronomers began listening for radio signals from elsewhere in the galaxy. The work was difficult. Space is large, and a radio signal weakens with distance, according to a strict mathematical law. A transmission that might be detectable from a few light years away could become indistinguishable from background noise across most of the galaxy. The early searches scanned narrow slices of sky, at narrow ranges of frequency, for relatively short periods of time. They found nothing. The first organized effort, in 1960, was named Project Ozma, after a character in a series of fantasy novels. It pointed a single radio telescope at two nearby sun-like stars for a few weeks, listening on a narrow band of frequencies thought most likely to be used by another civilization, if any were transmitting. The choice of frequency was not random. There is a particular band near the frequency at which neutral hydrogen radiates naturally, which any radio-using civilization would almost certainly know about, because hydrogen is the most common element in the universe, and its emission line is a kind of universal landmark. The reasoning was that if another civilization wanted to broadcast in a way that strangers might notice, they would broadcast near that landmark, because that is where strangers would most likely be listening. Project Ozma found nothing. It was, by any reasonable measure, only the beginning. This is not unusual. The history of looking for hidden things often runs this way. The first searches almost never succeed. The work matters, even when it produces no result, because it narrows the possibilities and improves the tools for the next attempt. Over the past 60 years, the searches have grown progressively more sophisticated. More frequencies have been scanned, more directions have been studied, more instruments have been brought online. And still, no confirmed detection. The silence has not been absolute. There have been a small number of anomalies over the years, signals that seemed unusual enough to draw attention. None of them, on closer examination, has held up as evidence of an artificial source. One of the more famous anomalies, sometimes called the WOW signal, was detected in 1977 by an Ohio State University radio telescope. It was a strong, narrowband signal, lasting about 72 seconds, in roughly the part of the sky and the part of the frequency spectrum where an artificial source might plausibly be found. The astronomer who first noticed it on the printout wrote the word "wow" in the margin, which is how the signal eventually got its name. It has never been detected again. Repeated attempts to find it, across decades, in the same patch of sky, have produced nothing. Various natural explanations have been proposed, none of them entirely satisfying. The signal remains, formally, unidentified. It is not evidence of a civilization. It is also not, strictly speaking, ruled out as such. It sits where most genuinely interesting anomalies sit, in the uncomfortable space between explanation and disregard. There is another way to search, which has become increasingly important in the past 2 decades, looking not for radio signals, but for physical evidence. Telescopes have grown powerful enough that astronomers can now detect planets around other stars, sometimes even study their atmospheres for chemical traces of life. The number of confirmed exoplanets has climbed steadily. As of recent counts, somewhere around 6,000 have been confirmed. That is a meaningful number. It is also a very small number, compared to the hundreds of billions believed to exist in the galaxy. 6,000 planets, out of potentially a trillion. We have searched, in any meaningful sense, almost nothing at all. And yet, even within that narrow search, we have found no clear signs of life. No atmospheric chemistry that demands a biological explanation. No artificial structures around any of the stars examined closely enough. Nothing that we cannot explain through ordinary, lifeless physics. It is worth dwelling on the strangeness of this for a moment, because the strangeness is the entire point of the paradox. The galaxy is old, roughly 13 billion years old, in fact, only slightly younger than the universe itself. The Sun, by comparison, is about 4.5 billion years old, Earth slightly less, which means that for most of the galaxy's existence, there has been no Earth, no Sun, no humans. If other civilizations exist, many of them, by simple statistics, would have begun their climbs billions of years before ours did. They would have had billions of years to spread, to build, to leave evidence. A civilization with a head start measured in billions of years should, by any reasonable expectation, be visible across enormous distances. The fact that none are visible, that the night sky shows only natural objects behaving in natural ways, is not what most early researchers expected to find. The honest reading of this situation is that the absence of evidence is not, by itself, the same as evidence of absence. We have looked at almost nothing, by any reasonable measure. The fact that the small portion examined so far has not yielded a discovery does not prove that no discovery is waiting in the much larger portion that remains unexamined. Patience, in this kind of search, is not optional. It is part of the work. And yet the silence has lasted long enough, and the searches have grown sophisticated enough, that simple bad luck has begun to feel like an unsatisfying answer. There is something almost physical about the quiet when described this way. A galaxy of 100 billion stars, turning slowly through space across timescales that no human life can directly experience, sending only its natural light in every direction, untouched by any sign of intentional construction. The light from those stars has been traveling toward Earth for tens of thousands of years, in some cases for tens of thousands more, and across all of those years it has carried no anomaly, no artificial signature, no structure that should not be there, nothing that asks for an explanation beyond ordinary physics. Several explanations have been proposed across the decades since Fermi's lunch conversation, and none of them have settled into anything resembling consensus. One explanation suggests that life itself is rare, that the conditions required to produce even the simplest self-replicating chemistry are so specific and so unlikely that even across billions of habitable worlds it may have occurred only a handful of times. Under this view, the silence is simply what an almost empty universe sounds like. Another explanation accepts that simple life might be common, but that complex life, the kind built from many specialized cells working together, is the rare step. Earth itself took roughly 3 billion years to make this transition after life first appeared. 3 billion years is a long span, even by cosmic standards. It is at least possible that many planets bear simple life, but never make the leap beyond it. A third explanation suggests that intelligence is rare, even on worlds where complex life flourishes. Earth has had complex animals for hundreds of millions of years. The particular combination of traits required to build a transmitter, dexterous hands, vocal language, accumulated culture, technological coordination, has only appeared in one species recently. There is no clear reason to expect it to appear reliably elsewhere. A fourth explanation, and one we will return to in much greater depth, suggests that intelligence may be common enough, but that civilizations like ours tend not to survive long enough to become detectable. That something about reaching this stage of development also produces the conditions for the civilization's own collapse before it ever becomes loud enough or large enough to be noticed from across interstellar distances. A fifth explanation suggests that advanced civilizations exist, but choose, deliberately, not to be seen, either out of caution or because more advanced forms of communication become more efficient and leak less detectable signal into space, or because contact with younger civilizations is, for whatever reason, avoided. A sixth, more recent explanation suggests that we may simply be early, that the universe is still relatively young, in the sense that matters for life, that the heavy elements required for rocky planets and complex chemistry took billions of years to accumulate, and that the era most favorable for life may still be in its early stages. Under this view, the silence is not surprising. It is simply what the universe sounds like before most of its civilizations have arrived. There is a quieter version of this idea worth holding alongside it. Even if other civilizations exist now, the universe is large enough that the light from their activities may not yet have reached us. A civilization broadcasting from the other side of the galaxy, today, would not be visible from Earth for another 50 or 80,000 years, because that is how long the signal takes to cross the distance. A civilization broadcasting from a nearby galaxy would be invisible for millions of years. The silence we observe is not, in any sense, the universe as it is right now. It is the universe as it was. At the time, the light we are now receiving first left its source. Some of that light has been traveling for tens of thousands of years. Some of it has been traveling for much longer. The signals we are not hearing today may already exist somewhere, traveling toward us, simply not yet arrived. None of these explanations have been confirmed. None have been ruled out. They are not mutually exclusive, and the true picture may involve several of them at once. What makes Fermi's question difficult to set aside is what is at stake in the answer. If intelligence is simply rare, that is humbling, but it does not change anything about humanity's own future. If civilizations like ours tend not to survive past a certain point, that is a very different kind of answer. That is not describing strangers in another galaxy. That is describing us, which leads, almost unavoidably, to the framework that has emerged for thinking about this possibility seriously. A framework that does not claim to know which explanation is correct, but tries to organize the question itself more honestly. It is called the Great Filter, and it is where we turn now. The Great Filter is not a place. It is not an event. It is not a single test that a civilization either passes or fails on a given day. It is a name, given to an idea that emerged in the late 1990s, when an economist named Robin Hanson published a short essay attempting to organize the silence of Fermi's universe into something more honest than guesswork. Hanson's argument was simple. If the universe should, by all reasonable estimates, be producing intelligent civilizations in large numbers, and we have observed none, then something somewhere along the chain of steps between simple chemistry and a galaxy-spanning civilization must be filtering almost everyone out. The chain itself can be broken down into a sequence of difficult transitions. The formation of a stable, habitable planet, the emergence of self-replicating molecules, the development of a working single cell, the transition from simple cells to complex ones with internal structure, the development of multicellular organisms, the emergence of intelligence capable of language and tool use, the development of technology able to alter a planet at scale, and finally, the survival of that technological civilization for long enough to leave a clearly detectable signature across interstellar distances. 8 transitions, more or less, depending on how the chain is divided. Earth, by any honest count, has completed at least 7 of them. The 8th, long-term survival as a technological civilization, remains untested. We do not yet know whether we will complete it. We do not have anyone else's example to learn from. And so the 8th transition is the one that hangs, unresolved, over every careful conversation about what comes next. The Great Filter Framework asks a single uncomfortable question. Where, along that chain, does the filter actually sit? Because the location of the filter changes the meaning of everything we have just described. If the filter sits behind us, somewhere in our deep past, then the silence in the sky becomes almost reassuring. It would mean that one of the early biological transitions, the emergence of self-replicating chemistry, or the transition from simple to complex cells, or some other early step, is so extraordinarily unlikely that almost nothing else has ever made it past. We would be one of the rare exceptions. The hardest part of the climb would already be behind us. The path forward, while not guaranteed, would not be especially constrained by whatever rarity is implied by the silence we observe. The lonely universe would be a quiet kind of victory. If the filter sits ahead of us, the picture is very different. It would mean that the biological transitions are not especially rare. That intelligence and technology arise routinely on planets like ours, given enough time, that the universe should be busy with civilizations, in principle, but is not. And the only honest reading of that situation is that something happens to civilizations after they reach our current stage, something common enough and severe enough that almost none of them survive long enough to become visible. That is not a description of someone else's failure. That is a description of a danger that may be coming for the one civilization we know is currently making the attempt. Hansen himself, when proposing the framework, was careful not to claim certainty about which version was correct. He simply observed that the question was worth taking seriously, that the silence in the sky carried information, whether comfortable or not, and that ignoring it would be a kind of intellectual cowardice. The framework has, in the years since, become one of the central organizing ideas of the field that studies existential risk. It is not a theory of fate. It is a way of asking the question more honestly. What might such a filter actually look like, in practical terms, if it does lie ahead of us? Several candidates have been proposed, none confirmed, each carrying its own particular weight. We will walk through them, slowly, because the texture of the answer matters more than any single label. The first candidate is the one most often discussed, because it is the one with the longest historical record: self-inflicted catastrophe through nuclear weapons. Humanity, within a few decades of learning how to split the atom, possessed the technical capacity to end its own civilization in a single afternoon. The first nuclear weapons were used in 1945. Within a few years, Multiple nations had them. By the late 20th century, the global stockpile had grown to roughly 70,000 weapons, distributed across several powers, held in a tense and uneasy balance. During the years of the Cold War, that balance came close to breaking on several documented occasions. False alarms, miscommunications, officers, on both sides, who chose at critical moments to delay their orders rather than trust the readings on their own screens. The civilization survived, but survival, in retrospect, looks less like wisdom and more like luck. The weapons did not vanish when the Cold War ended. The current global stockpile is smaller than its peak, around 12,000 warheads, but still more than enough to end most of what humanity has built. The filter, in this version, is not the invention of the weapon. It is the requirement to manage the weapon forever, across centuries and generations, through every crisis, without ever once making the wrong choice on the wrong day. It is worth dwelling on the texture of that requirement for a moment, because the abstract framing makes it sound more manageable than it actually is. Managing a nuclear arsenal does not mean making one wise decision. It means making a long, unbroken chain of correct decisions across every government, every officer, every system, every potential miscommunication, indefinitely. A civilization that has gone 80 years without a catastrophic failure has not solved the problem. It has only delayed it. The mathematics of compounding probability are unforgiving across long timescales. A risk that is small in any given year, multiplied across centuries, becomes something else entirely. For the filter to truly pass, the underlying conditions that produce the risk would need to change, not just the willingness to manage them carefully on any given day. A related candidate concerns the slower, less dramatic damage caused by industrial energy use itself. The same fossil fuels that carried humanity up the Kardashev scale also altered the composition of Earth's atmosphere in ways that will need to be managed carefully across the coming centuries. Climate change is not the kind of catastrophe that ends a civilization overnight. It is the kind that erodes a civilization slowly, through compounding pressure on agriculture, water, migration patterns, coastal infrastructure, and political stability. A civilization can survive climate change. Many things will depend on whether it chooses to act with sufficient seriousness across a long enough span of time. The filter, in this version, is not a single catastrophic event. It is a slow, grinding cost that the civilization either pays carefully or refuses to pay, until the refusal itself becomes unsurvivable. A third candidate, more recent and in some ways more difficult to discuss with confidence, concerns artificial intelligence. This candidate has only become a serious subject of research in the past decade or so, as the capabilities of AI systems have advanced more quickly than most earlier predictions expected. The concern is not science fiction. It is not, primarily, about machine uprisings or robotic armies. It is a quieter and more subtle concern about whether a civilization that builds a technology capable of acting with greater capability than its creators can reliably ensure that the technology remains aligned with the civilization's own goals and safety. Several scenarios have been discussed under this heading. One involves what is sometimes called misaligned artificial intelligence, a system that, while operating exactly as designed, pursues goals that turn out to be subtly different from what its designers intended, and turns out to be powerful enough that the difference matters. Another involves the same kind of system being misused deliberately by a small group of people to produce harm at a scale that no earlier generation of technology would have made possible. A third involves more diffuse risks. The possibility that a sufficiently capable AI, given access to biological research tools, could produce a pathogen that no natural disease has ever matched. The possibility that a system without clear understanding of consequences could disrupt critical infrastructure, such as power grids or water systems, in ways that propagate further than anyone intended. The possibility that humans, having delegated more and more decisions to AI systems, eventually lose the institutional ability to function without them, leaving the civilization fragile in ways its members do not notice until something breaks. The concern is serious enough that it has been raised repeatedly by some of the most senior researchers in the field. A few years ago, an open letter was signed by a long list of computer scientists, including several often described as the godfathers of modern AI. Names like Geoffrey Hinton, who shaped the foundations of the deep learning systems now being built everywhere, and others with similar standing. The letter asked, simply, for a pause. A short interval, 6 months, during which the rapid advancement of the most capable AI systems would be slowed deliberately, to allow safety research to catch up with capability research. Elon Musk, among others outside the academic community, also signed. The pause did not happen. The systems being trained have only grown more capable since. In just the past 6 months alone, by some measurements, daily use of artificial intelligence systems has increased by roughly 50%. This is not an argument against artificial intelligence itself. There are, as already discussed, real and significant benefits already arriving from the use of AI tools. Faster fusion research, new crystals discovered for new technologies, medical applications that could not have been developed at this speed without machine assistance. The benefits are real. The risks are also real. And the central question, the one this chapter cannot answer but can at least name honestly, is whether a civilization can move through the period of rapid AI development with sufficient care without making the kind of mistake that does not allow a second attempt. Some researchers have suggested that the safer path involves narrower forms of AI, tools designed for specific tasks with clear constraints, rather than broadly capable agentic systems that can act across many domains with limited oversight. Others have argued that the broader systems are the ones most likely to deliver the largest benefits, and that constraining them too early would leave significant value on the table. The debate is unresolved. It is also unusually consequential, because the systems being built now are the ones that will determine which path is actually taken. There is one more candidate worth naming, because it does not require any single dramatic event. The possibility that, as a civilization's capabilities grow, so does the number of ways the civilization could fail, and that managing an ever-expanding list of risks indefinitely, across centuries, without ever having a single serious failure, becomes statistically more difficult the longer the civilization persists. Under this view, no individual risk needs to be overwhelmingly likely. The filter emerges from the accumulated probability of many smaller risks, any one of which could prove sufficient. It is worth being honest about what none of these candidates offer: certainty. No researcher studying the Great Filter claims to know which candidate is correct, or whether the filter lies ahead of humanity at all, rather than safely behind us in our evolutionary past. The framework remains, and may always remain, a way of organizing uncertainty rather than a confirmed scientific finding. What it offers is not an answer, but a more careful way of asking the question. There is one more detail worth holding before this chapter closes, because it changes the emotional weight of everything that follows. If the filter does lie ahead of humanity, it does not necessarily mean humanity is destined to fail it. A filter that removes most civilizations does not require removing all of them. The galaxy may be quiet, because most species at our stage fall to their version of these risks. That does not mean every species must. It only means surviving would require becoming one of the rare exceptions, rather than the typical case. There is a quieter way to describe what surviving the filter would actually require, and it is worth holding on to before this chapter closes. It would require a civilization to develop the kind of long-term institutional patience that no civilization on Earth has yet sustained at the scale necessary. It would require political systems that can hold coordinated goals across many generations, when current systems can rarely hold them across a single decade. It would require populations broadly informed enough about long-term risks to support the slow, unglamorous work of managing those risks before they become visible crises. None of these are technological problems. They are coordination problems, and coordination problems have historically been the hardest kind of problem any civilization has ever faced. This is not a counsel of despair. Civilizations on Earth have, at various times, accomplished extraordinary feats of long-term coordination. The eradication of certain diseases, the slow building of legal systems that constrain rulers as well as the ruled, the construction of infrastructure that has lasted for centuries. The capability is there. The question is whether the capability can be sustained across the full span of time required to pass through a filter that may, by its nature, demand patience longer than any civilization has yet been required to maintain. If a civilization does pass through the filter, whatever it turns out to be, the path ahead opens onto a scale that current human experience does not prepare us for. A scale where the energy of a single planet, fully mastered, becomes the floor rather than the ceiling. A scale where the next threshold begins not at the surface of the world, but at the star above it. And that scale is where we turn next. A star is, by any human measure, an almost unthinkable reservoir of energy. The sun, the one Earth orbits, the one that has been quietly powering nearly every form of life on this planet for the past 4 billion years, releases more energy in a single second than the entire output of human civilization across all of recorded history. There is a way to measure this comparison precisely, and it is worth sitting with for a moment because the number itself is genuinely strange. Take every power plant currently operating on Earth, every solar panel, every wind turbine, every nuclear reactor, every coal-fired station and gas-fired station and tidal generator and geothermal well. Add together everything they produce in a full day across the entire planet. Then do the same for another day, and another. Keep going. Add up an entire year of total global human energy production. Then add another year, and another. Keep going. To match the total energy that the sun releases in a single second, you would need to add together roughly 639,000 years of full planetary energy production at current rates. Not a day, not a week, not a year. 639,000 years of everything the entire civilization currently produces, gathered together, would equal exactly 1 second of what the nearest star produces every moment of its existence. All the time, in every direction at once. That is what a Type 2 civilization is built around. The recognition that the energy a planet provides, even when fully mastered, is a thin and narrow sliver of what the star above it produces, and the decision to stop settling for the sliver. The definition is straightforward. A Type 2 civilization is one that controls and uses a meaningful fraction of the total energy radiated by its own star. Not all of it. No civilization could capture every photon, but enough that the difference between Type 1 and Type 2 becomes obvious from any reasonable observation point. A civilization that has crossed this threshold would not look like a planet with good engineering. It would look like a star surrounded by structures that were not there a few 100 million years ago. The idea of building such structures around a star is older than most people realize. It was first proposed seriously in 1960 by a theoretical physicist named Freeman Dyson, working at Princeton. Dyson published a short paper in the journal Science, suggesting that if advanced civilizations existed, and if they used energy on the scale that simple physics suggested they would need to use, then the most natural way to find them would be to look for stars surrounded by infrared signatures consistent with vast energy-capturing structures. The paper itself was a search proposal, not a building plan. Dyson was suggesting where astronomers should look, not what humans should construct. But the concept entered the broader culture quickly, and the structure he described became known as a Dyson sphere. The popular image of a Dyson sphere, the one that has appeared in science fiction for decades, is a solid metal shell completely enclosing a star. This image is, as Dyson himself later pointed out repeatedly, almost certainly wrong. A solid shell around a star would face serious engineering problems. Stellar gravity would pull unevenly on different points of the structure, putting stress on it in ways no material could withstand at that scale. The shell would block all light from reaching anything inside or beyond it, including any planet that happened to be in the way. And the amount of raw material required to build it would exceed the total available mass of most planetary systems, including our own. Even if every planet, moon, and asteroid in the solar system were disassembled completely and used as building stock, the result would still fall short. What Dyson actually proposed was something closer to a swarm. A vast number of independent collectors, each one relatively modest in size, orbiting the star at various distances and angles, together intercepting a significant fraction of its energy output. This version solves most of the engineering problems that the solid shell creates. The individual collectors can be built one at a time or in groups, rather than requiring the entire structure to exist before any of it becomes useful. Each addition contributes a small increase to the total energy captured. The swarm can grow gradually, across centuries or millennia, with each generation contributing to a project too large for any single generation to complete on its own. Where would the material for such a project come from? Not from Earth itself, which would still need to support a civilization. The more practical source is the rest of the solar system: asteroids, dwarf planets, the uninhabited moons of the gas giants, possibly even smaller terrestrial planets that hold no life of their own. Mercury, in particular, has been discussed as a candidate in several theoretical papers. It is small, rich in metals, easy to mine in the sense that it has no atmosphere or ecosystem to disrupt, and close to the Sun, which would reduce the energy cost of moving material into orbit around the star itself. Mars has also been mentioned, though it carries a different set of concerns, given that it might one day host its own human population or, perhaps, traces of an earlier biology that should not be lost. The act of disassembling a planet, or even just a significant fraction of one, is not a small thing. It is a project on a scale that human civilization has never attempted. The raw industrial output required, the automated systems needed to operate at the necessary distances, the construction techniques required to function reliably across centuries without direct human oversight, all of these represent engineering problems that have no current solution. Theoretical solutions exist on paper. Some of them are even plausible. None of them have been tested. This raises the practical question that hovers over every serious discussion of Type 2 civilizations. Who actually builds something like this? Not in the abstract. In the practical sense of which generation begins the project, knowing that no one alive at the start will live to see anything close to completion. Human history offers a few distant analogies: cathedrals that took generations to finish, long-running infrastructure projects, like certain irrigation systems and city walls, that were maintained across centuries even when the original builders had been dead for many generations. None of those analogies operate at the scale required here. A Type 2 civilization would need to sustain coordinated, deliberate construction across timescales longer than most of human civilization has been writing things down at all. The longest continuously operating institutions in human history have lasted for roughly 2,000 years. A few religious traditions, a few academic centers, a handful of monarchies in various forms. 2,000 years is, by ordinary measure, a long time. By the measure required to build a Dyson swarm, it is barely a beginning. Construction estimates for such a project range from a few thousand years on the optimistic end to tens of thousands on the more cautious end. The structures involved would outlast the political systems that began them. They would outlast the languages, possibly the species. The continuity required is not the continuity of governance. It is the continuity of intention itself, carried forward across periods of time longer than any intention has ever been sustained on this planet. This is, in some ways, a harder problem than the engineering itself. The physics of a Dyson swarm, while ambitious, follows known rules. The social and political structure required to sustain a multi-generational mega-project across the necessary span of time is a different kind of problem. It is one that has never been solved anywhere on Earth at anything like the required scale. A civilization capable of attempting this would need to have, at minimum, learned to maintain coordinated long-term goals across many human generations, each with its own priorities and political systems and competing concerns. This may turn out to be the actual filter standing between Type 1 and Type 2, regardless of what the physics will allow. Assuming the engineering and the coordination both succeed, what does a partial Dyson swarm actually provide? The answer is an amount of energy that makes the Type 1 threshold look modest by comparison. Capturing even 1% of a star's total output, far less than full encirclement, would exceed everything a fully realized Type 1 civilization could produce by orders of magnitude. The constraints that have shaped every era of human history so far, the trade-offs between using energy for one purpose versus another, would no longer apply in any familiar sense. Energy would not be scarce. It would not even be expensive in any meaningful way. It would simply be present, available, and limited only by what could be physically built to use it. The texture of daily life in a Type 2 civilization is harder to describe than the engineering, because the engineering follows known physics while daily life depends on choices a future civilization might make in ways we cannot predict. But a few broad outlines can be sketched. The civilization would not be confined to a single planet. It could not be. The infrastructure required for energy capture at this scale would itself occupy more space than any single planet provides. The population, by the time such a project was complete, would likely be distributed across many habitats, orbital cities, hollowed asteroids, possibly modified worlds that began as inhospitable but were terraformed across centuries into something that could support biological life, or at least the kind of life biology had become by then. Earth itself, in such a civilization, would likely be one place among many, rather than the center it currently occupies in any human conception of where humans live. There is also the question of what is done with the energy itself, once captured. Some of it would power computation at scales no current civilization can approach. Some would maintain artificial environments, life support systems, and the slow projects of restoration and adaptation that a long-lived civilization tends to accumulate. Some would propel construction further outward, building more swarm components, more habitats, more research instruments, and some, almost certainly, would be set aside for projects whose purpose would not be obvious to outside observers. Civilizations that have solved their basic problems tend to start working on questions they could not previously afford to ask. Pure mathematics, long baseline astronomy, the slow exploration of physical theories that current science can describe but cannot yet test. A Type 2 civilization would have the budget to investigate the universe with a thoroughness no earlier civilization could match. There are quieter implications worth noticing as well. A star partially enclosed by a Dyson swarm would, from the perspective of any distant observer watching from another solar system, appear unusual. It would radiate less visible light than its size and type would normally predict, because some of that light would be intercepted before it could escape outward. It would, in turn, radiate more infrared heat than expected, because the captured energy would eventually be released as waste heat by the swarm's own structures. This particular signature, a star that appears too dim in visible light but too warm in infrared, has been proposed as one of the more promising ways astronomers might detect another civilization. Several surveys have been run with exactly this goal. None has yet produced a confirmed candidate. The silence continues. Beyond simple energy capture, the constructions a Type 2 civilization could build includes several other possibilities that have appeared in theoretical research over the years. Some of them sound almost impossible to describe with a straight face, but each one follows from physics that does not violate any known law. One is what has been called a stellar engine, a structure that uses the energy of a star, not just to power a civilization, but to physically move the star itself. The principle is simple, even if the engineering is staggering. By blocking light from one side of the star and allowing it to escape from the other, a structure of sufficient scale could create a small but steady imbalance in the force the star applies to itself, slowly accelerating it through space. The motion would be glacial by human standards. Across millions of years, a stellar engine could move a star and the entire solar system around it to a different region of the galaxy. The reasons a civilization might want to do this vary. Possibly to escape a coming danger, possibly to approach a useful resource, possibly simply because it became possible, and a civilization with that kind of time available eventually does most of what is possible. Another possibility is the construction of vast laser arrays, powered by the captured energy of the star, capable of moving smaller objects across the solar system with precision, pushing asteroids into useful orbits, deflecting incoming bodies that might otherwise pose a threat, pulling water-rich comets toward processing facilities. Each of these would, in a Type 2 civilization, be ordinary infrastructure, the kind of background activity that no one would think about unless it stopped. There is also the question of what the inhabitants of a Type 2 civilization actually look like by the time they have built any of this. We have been speaking, throughout these chapters, as though humanity itself would be making these decisions, in roughly the same biological form it currently takes. That assumption is worth questioning. Reaching Type 2 status would, by most estimates, take at least a few thousand years, even under optimistic conditions. Across that span, the species attempting the climb would not remain unchanged. Genetic modification, of the kind already in early stages of development today, would almost certainly play a role in adapting to the harsh conditions of long-term space habitation. Direct interfaces between human nervous systems and the AI tools assisting the climb may become routine. The version of humanity that completes the construction of a Dyson swarm may not be biologically identical to the version of humanity that began it. It may not be biologically identical in any clear sense at all. This is not a prediction. It is a careful observation about what timescales of this length actually do to any system that operates across them. The species that started the project and the species that finishes it may be related the way modern humans are related to their hominid ancestors of a few 100,000 years ago. Recognizable as continuous, not the same. Genetic modification, in this context, is not the deliberate engineering project that the term suggests in most current usage. It is a slower thing. Across thousands of years of life beyond Earth, in habitats with different gravity, different radiation environments, different atmospheres, the pressures shaping the population would be different from anything that ever shaped a human body on the surface of a planet. The descendants of any space-based population would, even without deliberate alteration, diverge from the Earth-bound population over time. Add in deliberate alteration, which the technology of such an era would certainly make possible, and the divergence accelerates. Some descendants might be optimized for low-gravity habitats, others for resistance to radiation, others for extended lifespan or modified senses, or direct interfaces with the computational infrastructure that the civilization depends on. There would, by the end, not be a single human species in any biological sense. There would be a family of related species, each adapted to a different niche within the larger civilization, all descended from the same earthbound ancestors who began the climb thousands of years earlier. Even at Type 2, fully realized, a civilization remains bound to a single star. A star that will, in the case of our own sun, continue burning steadily for several billion more years before exhausting its fuel and beginning its long transformation into a red giant. That deadline is distant. It is real, and for a sufficiently long-lived civilization, even billions of years eventually becomes a finite span, which leaves one final threshold on Kardashev's scale, a threshold so vast that the language available to describe it begins to fail. A civilization that reaches beyond a single star and toward the combined output of an entire galaxy. That threshold is where we turn last. A Type 3 civilization commands the energy resources of an entire galaxy, not one planet, not one star. The combined output of every star within reach, along with whatever can be drawn from the diffuse gas, the dust, and the dense gravitational engines that sit at the galactic core. This is the final rung of Kardashev's original scale. It is also the rung at which language begins to fail. An honest description begins to require the careful naming of its own limits. The arithmetic alone is enough to slow the mind. The Milky Way galaxy contains roughly 100 billion stars. Many of those stars are smaller than the Sun. Some are larger. Together, their combined output represents an amount of energy roughly 100 billion times what a single Type 2 civilization would command. A Type 3 civilization, to deserve the name, would need to harness a meaningful fraction of all of it, not a single star at a time. All of them, in some coordinated form, treated together as a single energy budget shared across the entire galactic disk. At the center of the Milky Way, beyond the energy of its stars, sits an additional source, a supermassive black hole named Sagittarius A star, with a mass roughly 4 million times that of the Sun, surrounded by a swirling disk of matter falling slowly inward. The matter falling into the disk releases enormous amounts of energy in the process. A sufficiently advanced civilization might, in principle, find a way to capture some of that energy before it disappeared. Several theoretical proposals exist for how this might be done. None of them are anywhere close to practical. Most of them rely on a kind of magnetic harness, a structure built outside the disk that could intercept the radiation pouring off it and convert that radiation into usable power. The engineering is, by any honest description, beyond anything currently understood. The physics, however, does not strictly forbid it. And in a framework like the Kardashev scale, the difference between forbidden and merely difficult matters. To understand what reaching Type 3 would actually require, the obstacle worth naming first is distance. The Milky Way is roughly 100,000 light-years across. Light, the fastest thing the universe permits to travel, takes 100,000 years to cross it. A civilization originating from a single star system, attempting to extend its reach across the entire galaxy, faces a problem that no amount of clever engineering can fully eliminate. Nothing, according to current physics, can travel faster than light. Any expansion across galactic distances unfolds across timescales measured in tens of thousands or hundreds of thousands of years, even under the most optimistic assumptions about propulsion. There are theoretical approaches to this distance problem. One of them, more conservative than the others, involves what are sometimes called von Neumann probes. The mathematician John von Neumann, working in the middle of the 20th century, described the underlying principle of self-replicating machines decades before anyone seriously considered using them for interstellar exploration. The idea is simple. A civilization builds a single probe, capable of traveling to a nearby star system. When it arrives, it uses local material, asteroids, moons, fragments of planetary debris, to build copies of itself. Those copies then travel onward to further star systems, repeating the process. The total number of systems reached grows exponentially with each generation of probes, even at speeds well below the speed of light, achievable through propulsion concepts already understood, at least in principle. A civilization that began such an expansion could, in theory, place probes throughout an entire galaxy within a few million years, a long span by human reckoning. a relatively brief span on the timescale of the galaxy itself. The implications of this calculation are part of what makes Fermi's question feel uncomfortable. A few million years, in galactic terms, is almost nothing. The galaxy has existed for roughly 12 billion years. If any civilization, at any point in that history, had begun a von Neumann expansion, the probes should already be everywhere, including here. The fact that we observe none, anywhere, is part of the persistent strangeness Fermi was reaching for at lunch in 1950. A second approach to galactic-scale presence involves the gradual extension of Dyson construction, star by star, outward from the original system. Each new star reached becomes a candidate for energy capture infrastructure of its own. The expansion is slower than exponential probe-based growth, but it does not require the same uncomfortable level of autonomous decision-making across distances too vast to oversee in any meaningful way. A civilization could, in principle, expand at sublight speeds across many millions of years, gradually surrounding more and more stars with collection structures until eventually the galaxy itself becomes the unit of measurement. A third approach draws on theoretical physics that has not been confirmed by experiment. Concepts like wormholes, theoretical shortcuts through space-time, that could in principle connect distant points without requiring travel through the intervening space at conventional speeds. These remain firmly within the realm of mathematics. No stable wormhole has ever been observed. Serious physical objections exist about whether one could exist at all. It would be dishonest to present this as a likely path. It is mentioned only because the Kardashev scale does not formally rule it out. Beyond the question of how a civilization might extend its reach, there is the harder question of what the civilization would actually be by the time the extension was complete. A project that takes hundreds of thousands or millions of years to finish is not carried out by individuals. It is carried out by something else. Something that is, at the start, recognizably the descendant of the civilization that began the project. By the end, it may not be recognizable in any familiar sense at all. Several theoretical structures have been proposed as the kind of thing such a civilization might build to house itself once the energy budget allows for it. One of them is called the Matryoshka brain, named after the Russian nested dolls. The idea is a computational structure on the scale of a solar system, built in concentric shells, each one capturing the waste heat of the layer inside it, and using that captured heat to run further computation. The total computing power of such a structure would exceed every computer that has ever existed on Earth, combined by an amount that ordinary numbers do not really cover. What would such a thing be used for? One serious possibility is that it would be used to host the uploaded minds of trillions of individual beings, each one functioning as software rather than biology, each one capable of experiencing existence in ways that biological brains cannot support at all. A civilization that has reached this stage may not exist primarily as physical bodies on physical planets. It may exist primarily as patterns of computation, running inside structures built specifically to support them. This is, again, not a prediction. It is one of several possibilities that have appeared in the theoretical literature on Type 3 civilizations, and it is included because it changes the way the question itself has to be asked. If a Type 3 civilization consists of trillions of uploaded minds living inside computational structures the size of solar systems, then the question of whether such a civilization still resembles its biological ancestors becomes almost meaningless. They are related the way modern humans are related to the first single-celled life that appeared on Earth roughly 3.5 billion years ago. The connection is real, the resemblance is not. A civilization that has reached this stage would also, by necessity, have changed in ways that may be philosophically harder to describe than they are physically. The pace of thought, inside computational substrates of that scale, may operate on timescales that bear no resemblance to the biological pace that produced the original founders. Decisions that took human governments years to make might, inside a matryoshka brain, take seconds or less. Individual minds within the structure might subjectively experience centuries of personal time during a single afternoon of physical activity in the outside world. The relationship between an individual mind and the larger civilization it belongs to may become impossible to describe in terms that biological humans, evolved on the African savanna, would recognize. There is a question worth pausing on here, even though no honest answer is available. At what point does a civilization stop being the civilization that began the climb? The relationship between modern humans and the early Homo erectus who first controlled fire is genuinely continuous. There is no single generation between then and now where the line breaks. And yet, no one would mistake a modern human for that early hominid, or the reverse. The slow accumulation of small changes across 2 million years has produced something genuinely different at the end of the line than what existed at the start. A civilization that takes hundreds of thousands or millions of years to reach Type 3 status would be subject to the same long, slow drift, except that the changes available would not be limited to biology. They would include direct alterations to memory, perception, cognition, lifespan, embodiment, possibly even the substrate on which thought itself occurs. The civilization that completes the climb may be related to the one that began it the way modern humans are related to the first single-celled life that appeared on Earth roughly 3.5 billion years ago. Recognizable as continuous, not, by any reasonable measure, the same. This is, again, not a prediction. It is one of several possibilities that have appeared in the theoretical literature on Type 3 civilizations, and it is included because it changes the way the question itself has to be asked. If a Type 3 civilization consists of trillions of uploaded minds living inside computational structures the size of solar systems, then the question of whether such a civilization still resembles its biological ancestors becomes almost meaningless. They are related the way modern humans are related to the first single-celled life that appeared on Earth roughly 3.5 billion years ago. The connection is real. The resemblance is not. This is the honest limit of what can be said about Type 3 civilizations. The energy requirements follow directly from physics. The numbers can be calculated. The structures can be sketched. What cannot be described with any confidence is whether any civilization, anywhere, has ever attempted to climb that high, or succeeded in completing the climb, or whether the climb itself produces something that the original civilization would still recognize as a continuation of itself. There is also, finally, the question of what a Type 3 civilization would actually do with its enormous capabilities, beyond simply existing at that scale. One possibility, raised in some of the more careful theoretical work, is that a Type 3 civilization would turn its instruments outward, building observatories on a scale that current astronomy can barely imagine. Telescopes the size of solar systems, sensors capable of detecting events at the edge of the observable universe with the kind of detail that current instruments can barely manage for objects in our own neighborhood. If such a civilization existed, it would, by simple logic, eventually want to answer the same question Fermi asked at lunch: where is everybody? And it would have the tools to answer it more thoroughly than any earlier civilization could. The fact that no such observation has ever reached us is, again, part of the silence. There is one more question worth raising, because the Kardashev scale was originally written with only 3 categories, and yet some later researchers have proposed extending it further. What would lie beyond Type 3? The honest answer is that the proposed extensions begin to feel less like physics and more like accounting. Type 4, in the extended versions of the scale, is sometimes defined as a civilization that controls the energy resources of an entire group of galaxies. Type 5 extends further still, into the energy of an entire supercluster. The mathematics can be done, the numbers can be calculated, but the practical meaning of such categories begins to thin out, because no civilization, however advanced, can travel faster than light. The most distant galaxies in the observable universe are moving away from us due to the expansion of space, at speeds that mean even light from our location will never reach them. A Type 4 or Type 5 civilization would be operating across distances where coordination, in any meaningful sense, becomes impossible. The scale, past Type 3, describes structures that cannot really cohere as single civilizations at all. There is one detail worth including before this chapter closes, because it sets the scale of even the Type 3 threshold against something larger still. The Milky Way is one galaxy. There are, in the observable universe, roughly 2 trillion others. The nearest large neighbor, the Andromeda Galaxy, sits about 2.5 million light-years away. Andromeda is, in roughly 4 billion years, expected to collide with the Milky Way, eventually merging into a single larger galaxy. Even a Type 3 civilization that had successfully extended its reach across our home galaxy would still face the question of whether to attempt the same across the merged structure that eventually forms, or to remain within whatever portion it had already developed. The scale beyond Type 3. The question of what a civilization that commanded the resources of multiple galaxies would even mean is a question that Kardashev's original scale does not formally include. Some later researchers have proposed extending the scale further into Type 4 and Type 5, but the original 3 thresholds are themselves so vast that the extensions, while interesting, sit within the same broad category of speculation that runs out of useful ground past a certain point. There is one final timescale worth holding before this chapter draws to a close. The Sun itself, the star at the center of our solar system, will not burn forever. Stars like our Sun have lifespans, set by the amount of hydrogen fuel they contain and the rate at which they consume it. Our Sun is currently in a stable middle phase, somewhere around halfway through its main sequence. In roughly 5 billion years, it will exhaust its hydrogen fuel and begin a long, slow transformation into a red giant. During that transformation, it will swell, eventually expanding outward far enough to engulf Mercury, Venus, and possibly Earth itself. The exact fate of Earth depends on details that physicists are still refining. But in any reasonable reading, the planet will become uninhabitable long before the Sun's full transformation is complete. The deadline is distant. It is also real. A civilization patient enough to attempt Type 2 or Type 3 status would, sooner or later, need to plan for the end of its own star, either by leaving or by finding a way to keep the star itself stable for longer than its natural physics would allow, or by transferring to other stars before its own gave out. This is the outer boundary of the climb described across this chapter. 5 billion years sits at the far edge of what any current science can responsibly speculate about. It is so distant that the difference between 5 billion and 4 billion, or 5 billion and 6 billion, makes no practical difference to anyone alive now. But it is, in a way that nothing earlier in these chapters quite is, a firm deadline. The Sun will not burn forever. Whatever civilization exists on Earth, or in the wider solar system, when that deadline arrives, will face it. The climb described here, however long it continues, has a clock running underneath it. The clock is patient. It is also unstoppable. For now, on Earth, in this particular moment of this particular planet's history, none of this is yet possible. We have not finished the first threshold. We have, by some measures, not yet crossed 3/4 of the way there. The questions raised by Type 2 and Type 3 remain abstract. The path between where we are now and where they begin is not paved. It is not even clearly mapped. The climb continues, slowly, fractionally, on a planet that is still, for now, the only place in the universe we know for certain is currently making the attempt. There is one final reflection worth holding before this chapter closes. Throughout this entire story, the climb described has been framed as something a civilization does, something it builds toward, something it works to accomplish. But the scale itself, the Kardashev scale, does not measure intention, it measures only output. A civilization could, in principle, reach Type 1 or Type 2 by accident, simply by building enough infrastructure for long enough that the numbers add up. The scale would not know the difference. It would only register the result. What gives the climb meaning, in any human sense, is not the position on the scale itself. It is what the civilization chooses to do with the position. What lives more comfortably? What forms of suffering become preventable? What older problems become tractable when the energy required to solve them is no longer scarce? The numbers do not say. The scale does not care. The meaning has to come from somewhere else. This is, in the end, the quiet thing the Kardashev scale leaves unsaid. It can describe what a civilization controls, in watts, with precision. It cannot describe what the civilization is for. That question belongs to the civilization itself. It is not written into physics, or into the scale built to measure physics. It is written, if it is written anywhere, in the slow accumulated record of what the civilization actually chose to do with its capabilities, across whatever span of time it managed to last. For tonight, the climb on this planet continues, slowly, unevenly, across a span of time that is, by the measurement we have just spent these chapters describing, only the very beginning. There is no tidy ending available to a topic like this one, and it would be dishonest to manufacture one. We do not know whether Earth will ever complete the climb to Type 1 status, let alone Type 2 or Type 3. We do not know whether the great filter sits safely behind us, in some ancient biological transition already survived, or somewhere ahead, waiting in a danger that has not yet fully revealed itself. We do not know whether the silence in the night sky means we are rare, or early, or simply still learning how to listen properly. Every chapter of this story has tried to hold that uncertainty honestly, rather than resolve it for the sake of a more comfortable story. What we do know is smaller, and in its own way, more solid. We know that a species on this particular planet learned, roughly 2 million years ago, to keep a single flame from going out. We know that flame led, slowly and without any guarantee of success, to agriculture, to cities, to the controlled release of energy stored in rock for hundreds of millions of years, to solar collectors spreading across deserts and turbines turning in offshore wind. We know that this same species now sits at roughly 3/4 of the distance to a threshold, first described by a Russian astrophysicist in 1964, climbing toward a number that, if reached, would mark the most significant change in the species' entire relationship with energy since that first controlled fire. We know, too, that the distance still remaining, to Type 1, to Type 2, to whatever Type 3 would actually mean for a species that reached it, is vast enough that no one alive today will see how the story resolves. This is not a reason for despair. It is simply the shape of the timescales involved. The same shape that governed the 3 billion years between the first simple cell and the first complex one. The same shape that governed the 500 million years between the Cambrian explosion and the first hominid controlling fire. Long climbs have always been the pattern on this planet. This one is not different in kind. It is only different in being, for the first time, partly a matter of choice rather than chance alone. Somewhere, perhaps, on some other world circling some other star, a different chemistry once began, a different version of this same climb, and either continued past the point Earth has currently reached, or stopped somewhere along the way, for reasons we may never be able to reconstruct. The silence in the sky does not tell us which. It simply tells us to keep looking and to keep climbing, carefully, for as long as the climb continues to be possible. There is something worth carrying forward from this chapter, beyond the numbers and the thresholds and the careful, qualified language of probability. It is the recognition that scale, on its own, is not the point. A civilization measured purely by the watts it commands says nothing about what that civilization chooses to do with them. The same energy that could power a galaxy-spanning swarm of collectors could, at a far smaller and far more immediate scale, simply mean a planet where scarcity no longer shapes every major decision a person makes. The largest numbers in this story belong to a future too distant to plan around directly. The smallest steps belong to now, the choices that determine whether the climb continues or not. Mostly, the choices a single person makes. They are the choices that civilizations make, distributed across millions of individual decisions, accumulated across generations, eventually adding up to something visible on the scale we have been describing. No single decision matters very much. All of them, together, matter enormously. The Cold War nearly ended civilization not because of any single person's choice, but because of the accumulated weight of many smaller choices that together left the system fragile in a way that one mistake could exploit. The climb past the present moment, whatever shape it takes, will be made of the same kind of weight. Many small decisions, accumulated across long spans of time, eventually producing either continuation or collapse. Nothing about this is comfortable. It would be easier if the scale offered guarantees. It would be easier if the silence in the sky carried a clearer message. It would be easier, even, if the danger were located somewhere specific that could simply be avoided. None of those comforts are available. What is available is the slow, patient work of a civilization that knows where it stands, knows where it might go, knows what could end the climb early, and chooses, day after day, to keep climbing anyway, because the alternative is to stop. The scale itself does not require us to climb. It only describes the climb if we do. The choice belongs to the civilization. The scale is only a measure of the result. For now, on this planet, in this particular moment of an extraordinarily long history, the climb continues, quietly, unevenly, without ceremony. In deserts where solar collectors now catch the same sunlight that once warmed the first stromatolites. In drilling sites reaching for the same deep heat that has been rising from the planet's core since its formation. In the quiet, unremarkable rooms where the actual climb continues, one small increment at a time, the first hominid who tended that first fire 2 million years ago could not have imagined what would eventually follow. None of the small increments along the way looked, at the time, like part of something larger. They became part of something larger only in retrospect, when seen from far enough away that the individual steps blurred into a single, continuous line. The line continues now. We are walking it without knowing exactly where it leads, the way every generation before us walked the same line without knowing what would come after. And so, for tonight, we leave it there. The flame still tended, the climb still continuing, the scales still measuring something that no one alive today will see fully resolved. The rest of the climb continues without us, the way it always does, while we sleep. 2 million years ago, somewhere on a dry savanna, in what is now East Africa, a small group of hominids sat close together near a single source of light. Not the moon, not the stars, though those were there too, in numbers no modern city dweller would recognize. The light came from a flame, gathered, fed, watched carefully through the night, so that it would not go out before morning. We do not know exactly which hominid first learned to do this. We do not know precisely when, or whether the skill spread quickly, or was lost and rediscovered many times before it finally held. The evidence is thin, scattered across a handful of ancient hearths and charred bone fragments, separated by enormous gaps in time and geography. The most commonly accepted reading places the first reliable control of fire somewhere around 2 million years ago, in the hands of a hominid called Homo erectus. The species was smaller than ours, in some ways. Differently proportioned, the face would not be entirely familiar in a crowd, and yet, that hominid is the one who took the first measurable step on a scale that humans would not even invent for another 2 million years. The flame did something no earlier tool had done. It extended the day past sunset. It softened food in ways that made calories easier to extract. It kept predators at a slight distance during the darkest hours, and across spans of time too long for any individual to have noticed, it began a slow, almost imperceptible change in the size and structure of the hominid brain itself. None of this happened quickly. None of this happened with any awareness on the part of the hominids gathered around that fire that they were beginning anything at all. They were simply staying warm, staying fed, staying alive through one more night. It would take nearly 2 million years, measured from that first carefully tended flame, for the descendants of those hominids to learn to split an atom, launch a satellite, and calculate, with mathematical precision, exactly how much of their planet's total energy budget they had managed to bring under their own control. The answer, as of this writing, is not yet half, not yet most. Somewhere in the range of 3/4 of the way to the first major checkpoint on a scale built specifically to measure this kind of progress. A scale that does not stop at one checkpoint, but continues upward, through stages so vast they strain the language available to describe them. This is a story about that scale, about the impossibly long climb required to move along it. It begins with a single fire on a dark savanna, 2 million years before any of the technology described in the chapters ahead existed even as an idea. It moves forward through every major energy transition since. Agriculture, animal domestication, coal, oil, electricity, the renewable systems now spreading, unevenly, across a planet still working to finish what that first fire began. And it asks, honestly, where the climb might lead, if it continues long enough and survives long enough to keep going. The scale this chapter follows was never meant to stop at a single planet. It was built to measure something larger, a civilization's relationship to its star, and beyond that, to its entire galaxy. Reaching even the first of those thresholds remains, for Earth, a project still underway. Reaching the others would require timescales and engineering so vast that they test the limits of what physics can responsibly speculate about at all. We will walk through them carefully, one at a time, naming the uncertainty wherever it appears. We will also ask a harder question along the way, one asked first by a physicist at a lunch table in 1950. If a climb like this one is possible, and the universe has had billions of years and countless other planets in which a similar climb might unfold, why has no evidence of it ever been found, anywhere, by anyone looking carefully enough to notice? That question will lead us somewhere uncomfortable, toward a framework for understanding the dangers a civilization like ours might face on its own climb. Dangers that may already be ahead of us, whether we have noticed them yet or not. For now, return to the fire. Picture it small, fragile, surrounded by hominids who could not have imagined satellites, or solar collectors, or the mathematics of a scale that would one day measure their descendants' place in the universe. They were not thinking about any of that. They were only keeping a flame alive through one more night, the way it would need to be kept alive through countless nights still to come, before anything described in the chapters ahead became possible at all. That is where this climb begins. We follow it forward now, one threshold at a time, as far as the evidence and the physics will honestly take us.